In this video, I'll be talking to you about the electromagnetic spectrum and prisms. Here is a picture of the electromagnetic spectrum. Before we get into the details, I first want to draw your attention to the purple box in the bottom right-hand corner. And I want to talk about how we in physics class are going to use the word light. In everyday language, light means the stuff we can see. But in physics class, the word light will refer to any electromagnetic wave along this spectrum. So it may be the light we see, that visible spectrum, which is shown as a rainbow in this diagram, but it might not be the light that we can see with our eyes. So let's break down this diagram. There's a lot going on here. This is something that you should be familiar with. And so in the middle here, these are the colors of light that our eyes can see. At one end, we have the blue-purple range of the spectrum, and at the other end, we have the red end of the visible light spectrum. Let's talk about what differentiates those. Really just the wavelength of the electromagnetic wave. Our eyes are wavelength detectors or frequency detectors for light waves. And so our brain interprets different wavelengths as what we see as color. So the red end of the spectrum is wavelengths around 700 nanometers, nano being times 10 to the minus 9 meters. This corresponds to a frequency of 4 times 10 to the 14 hertz. The other end of what we can see in the visible spectrum is blue or purplish light, which is 400 nanometers, and that corresponds to a frequency of about 7 times 10 to the 14 hertz. You'll notice that the inverse relationship between wavelength and frequency is shown here. Red is a longer wavelength but lower frequency. Blue is a shorter wavelength but higher frequency. We can also see that same idea in the wave picture shown above. Over here, near the radio wave end of the spectrum, we have very long wavelengths. But you can imagine that since the waves are so spaced out, as they traveled from left to right, you'd only see a crest every so often. Whereas at the other end of this picture, we have very short wavelengths. And so if we imagine this wave over here moving from left to right, they'll hit more often, boom, 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 because they're closer together. So in other words, we would see a wave crest more often or more frequently. So in other words, it has a higher frequency. Let's talk about the different classifications we give to different waves in the electromagnetic spectrum. The highest frequency, shortest wavelength light is gamma rays. And then the next lowest wavelength or next highest frequency is X-rays, and then ultraviolet, and then visible light, and then infrared, and then microwaves, and then radio waves. You'll notice that what we can see with our eyes is a very narrow portion of all of the different wavelengths that are out there, all the different frequencies that are commonly encountered. To help remind you of to help you out a little bit, some ideas that are useful is this word infrared. What does the word infra mean? It means below. And so below what? It means below red in frequency. So that can help you remember that red is the low frequency end of the color spectrum because we have stuff that lives below red. Then we have over here ultraviolet. Ultra meaning above. It's above violet. Above in what? Above in frequency. It's even higher in frequency than violet is. It's ultraviolet. Usually we classify waves by their frequency, or electromagnetic waves by their frequency. That's more common than talking about their wavelength. Of course, if you know one, you know the other, because speed is wavelength times frequency, and the speed of light in a vacuum is 300 million meters per second. So you need to be familiar with the electromagnetic spectrum. You should know that light is frequencies over a wide range, all the way from 100 hertz to 10 to the 24 hertz. All right, prisms are the other thing we're talking about in this video, and we'll connect them on the next slide, the two topics. But here we have a prism. Prism is something that uses refraction to separate out light, and it uses it given a certain geometry. So here we have a prism made of glass. It is a triangle, and we have air on either side of our glass. Here's some incoming incident light. This is the normal to that surface. And we know that light will bend toward the normal as it enters the slower, more optically dense glass. So we're going to get a refraction toward this normal line. That's what we have there. We're now at a new boundary that's at a different angle. There's the new normal line for that light ray. And we're entering, now light is going to speed up. And since it's going to speed up, it's entering that less optically dense air, it's going to bend away from the normal. Well, bending away from the normal at this angle looks like this. So we get refraction that bends toward the bottom of the screen twice because of the geometry of the prism giving different helpful normals for that goal. So that's what a prism's doing. It's refracting light. Why do you see rainbows with prisms? Well, this is a great animation. I love this GIF here. It's of the different wavelengths of light being separated out. And the idea is that different wavelengths of light will refract different amounts. So the short wavelength violet light will refract more than the long wavelength red light. A mnemonic to help you out with this is that violet veers vigorously. Violet bends more in a prism than red. Another way to say this is that the index of refraction for a material depends on the wavelength of light. So the index of refraction for red light in glass is 1.50817. The index of refraction for violet light in glass is 1.52136. They're different, right? They're not very different. So if we're not going to separate it out a lot, we might just say, on average, the index of refraction for glass is 1.5. But if we are going to want to look at how different wavelengths of light refract, we would need to know the index of refraction at that wavelength. That concludes this presentation on the electromagnetic spectrum and prisms.